So for our project, we decided to build an apartment price predictor for apartments around Evanston for first-time renters, like Northwestern students, find if their apartment is a good value or not. So we decided to collect data manually as we weren't allowed to use web scrapers given many terms of use policies. So we collected around 50 data points as around 30 data points is when the central limit theorem kicks in, and past that is a bit more of a buffer. So we decided to pick four core features, which were number of bedrooms, number of bathrooms, square footage, and that they have an in-unit laundry. And then these four features we found to be most correlated with the price. So first of all, we just ran a linear regression with our data that was clean. And then we used a normal equation in this and we manually calculated everything, which you can see in our results. So our R squared is pretty good, but our root mean square error is a little high at 608. But given that our data prices range from around $850 to around $6,700, $600 margin is not terribly high. And then for sanity check, we just ran a linear regression using sklearn's imported library, and then we can see we have the same results. So next up, we decided that it'd be probably good to split the data to see how our model would perform on data it hadn't quite seen before. So this is a pretty basic 80-20 split that is standard. And we decided to split the data so that there's 40 points for training, 40 for, 10 for testing. In our results, we can see that the training data, the R squared value is pretty good at 0.76. However, when we go to the testing data, we can see that the R squared score drops quite a lot. So this is probably telling us that our model is overfitting, which is expected given how our data set is only around 50 points.
Yeah, and also given that our original model was only linear, it's worth exploring the notion that apartment price features are likely nonlinear, and therefore we use a nonlinear model. So we decide to explore the random forest regressor, which takes a look at basically variance, and it tries to minimize variance as its cost function. So to implement this, we start with a regression tree, and within that class, we create a subclass called node, where basically each node stores the feature threshold couple if it's an internal node. If it's a leaf node, then it just stores a value. And so build tree basically does that. It builds up all the trees. So at each node, it cycles through all the feature indices that we select, and then it tries to find the best loss by sifting through all those features and trying a bunch of different thresholds, at which point it'll converge on a specific feature comma threshold pair, if you will. And the cost function it does to do that is the basically taking the variance of all the data points with a threshold with a value less than the threshold, and all the data points with a value higher than the threshold, takes the variance of the two, sums them up, and then tries to minimize that through all the iterations. And then the fit function basically does the fitting of the data to each tree, basically predicts, and then next we decide to create the actual forest class. So that takes a whole bunch of trees, builds them out, and then it bootstraps the data. So it picks with replacement 50 points from the data set, which increases the variance of each tree. But once we take the average of all the outputs, that will actually minimize the variance. So as you can see, we decided to implement it using using these classes. And what we found is that the R squared is actually much better when we train it on the entire data set, giving us 0.88. And our RMSE is actually about 30% less than our linear implementation. And then finally, but when we did data splitting, then we realized that R squared is about the same. And so that really tells us our biggest bottleneck is that low number of data points. If we had more time, more resources, maybe we could get a higher data set, maybe 200 to 300, given that there's around 500 apartments in Evanston. So that would give us a better sight over the overall population, if you will, of apartments in Evanston. And so that would be our biggest improvement for future improvements on this project. However, given our constraints and also our implementations, we believe that this data is promising in creating a better model for Evanston students to find on campus.